G'day team, welcome back to another mathematical induction video. So in the previous video we went over what a proof by mathematical induction sort of looks like, and we did some basic series, and now we're going to start looking at some more advanced and complicated examples. And you can see we haven't changed too much, except now we've got some powers involved. So the process is still going to be identical, but we're going to have to use some different math strategies to show that the left-hand side is the right-hand side when we get down to our P of k plus 1 case. So let's run through the proof together. So my P of n statement is 1 plus 4 plus 4 squared plus 4 cubed plus ... plus 4 to the power of n. That's my left-hand side. And we're trying to prove that that is equal to 4 to the power of n plus 1 minus 1 all over 3. Now it looks a bit more complex, but we're going to go through it together. So we're going to try and prove the base case using n equals 0, because for all n greater than or equal to 0, we can use the base case 0. So on the left hand side I've got 4 to the power of 0, which is just 1. And on the right hand side I've got 4 to the power of 1 minus 1 all over 3, which is equal to 1 as well. Therefore, P of 0 is true. Okay, so we're getting a little bit less scaffolded now, and we're going to have to start putting in some of our final statements here. Now, we're going to assume PK is true. Now, PK is just 1 plus 4 squared plus 4 cubed plus ... plus 4 to the power of k is 4 to the power of k plus 1 minus 1 all over 3. That is my PK statement. Now we're going to look at my P of k plus 1. So I'm going to be a little bit sneaky and steal all of this and duplicate it down here. But we've also got a 4 to the power of k plus 1. And we're going to say that that is equal to 4k plus 1 plus 1. Okay, so I'm putting in k plus 1 instead of k, minus 1 all over 3, but we know 1 plus 1 is just 2. Now what we're going to do, we're going to prove this is true. So just like before, we can notice that this here is P of k. So we can say all of this stuff here is equal to the right-hand side of PK. So my left-hand side has actually become 4, oh, I'm in red. Let's get rid of that. 4k, black. So 4 to the power of k plus 1 minus 1 all over 3 plus 4 to the power of k plus 1. And we say that is equal to 4, k plus 2, take 1, all over 3. Now, this is getting a little bit more complex, but I've just sort of ignored this little bit here for now, and I'm sort of going to solve both sides simultaneously. Okay, so easiest thing to do is probably get rid of these divide by 3's, and I'm going to times everything by 3. So if I times this whole side by 3 and this whole side by 3, I get that 3 and that 3 cancel out, and that 3 and that 3 cancel out. So I'm left with 4k plus 1 minus 1 plus 3 times by 4 to the k plus 1 equals 4 to the k plus 2 take 1. Now what I want to do is start sort of manipulating this so we can sort of make it look similar. You'll notice I've got minus 1 on both sides, so they can also cancel out. All right, now 4 to the power of k plus 1, I can split up to be 4 times by 4 to the power of k. And I'm going to do the same thing with this side. I've got 3 times by 4 times by 4 to the power of k, and 4 squared times by 4 to the power of k. Now, what we want to do, we want to take out a factor of 4 to the power of k on this side. So I've got 4 to the power of k. In this first term, I'm left with just 4. In this term, I'm left with 16. So I've got 4 plus left with 12, getting ahead of myself. And on this side, I've got 16, 4 to the power of k. Now, 4 plus 12 is just 16, so I've got 16 times 4 to the power of k equals 16 times by 4 to the power of k. And they are the same, so left-hand side equals right-hand side, which is what we wanted to show. Therefore, pk plus 1 is true. And then we write our final statement. So since p naught is true, and p of k plus 1 is true whenever pk is true. Okay, so we use pk to prove pk plus 1. Because of those conditions, Pn is true for all n greater than or equal to 0. That was my initial condition right back up the top here. So Pn is true for all n greater than or equal to 0 by the principle of mathematical induction. All right, done. So you can see there's a few new algebraic strategies that we're using, some index laws, getting rid of denominators of fractions that are a little bit different to the example we went through in the last video, but the idea and the process is still the same. So have a crack at some of those questions and we'll see you in the next video. Thanks, guys.